This video is an introduction to what's known as the Biot Savart Law. This law is an integral law to determine the magnetic field of a distribution of currents. So what I mean by a distribution of currents is the fact that here I could have a line of current number 1, and I could have a line of current number 2, say be a cycle, right, like a circuit. And then maybe there is some current heading out of the page, I3, and some current, say, heading into the page, I4. And you know that currents, right, they run through space from one place to another along some interesting line or shape, you know? Like this is a cycle, it could be a circle or something. These are straight line currents, I3 and I4. I3 headed out, I4 headed inwards. And here is some arc, you know, some sort of shape, and I'm only drawing a short section of it. You know, it could go on. And here's a fourth current, I1. And it's distributed in space, right? These various currents are at different places in space. And we can ask, over here, right there, what is the magnetic field? What's the net magnetic field due to all of the currents? Because each current by itself is a source of magnetism, and all of these sources of magnetism put their magnetic field value at this location here, right? And this is what Biot Savart shows us how to do, right? So the sense in which it's an integral law is it's going to show us how to calculate a small contribution to the magnetic field, right? So this is what we're going to write down first. We're going to write down an expression for the small contribution, and to get the net magnetic field, we actually just use the superposition principle. So the superposition principle says, add it all up, right? Where the integral is over the distribution of currents. That is, we have to do an integral that goes all over everywhere in space where there is current, and we add up the contribution to the magnetic field at some location, right? For electric field, I've been calling it a P, a place P or position P, right? So what is the contribution to the magnetic field at the place P due to the various currents distributed at various other places in space, right? So Biot Savart has a pretty interesting look to it. So of course there's going to be some physical constants and stuff. So the way it typically gets written is if you have a mu naught over 4 pi. I have to tell you what mu naught is in a second. It's not got to do with magnetic dipole moment, which is a topic from a previous chapter or some previous videos. And then it's got I, and then a really complicated thing. It looks complicated. You just have to figure out how to use it. There is a vector called ds, and its cross product with an r hat, and then divided by an r squared. So notice that what I have written down is actually a vector, but its length or its amount is infinitesimal in the calculus sense. So it makes sense that I can integrate it. That is, I can add up an infinite number of these infinitely small amounts of magnetic field and still expect a macroscopic but finite value of field. The B field has an SI unit of Tesla. So somehow all of these details inside of this expression, they amount to the units of the Tesla if you put in SI units. So here is I have to show you what each of these terms are, or these factors in this expression, but it is a vector because I have the vector cross product between a vector called ds and a vector called r hat, right? Okay, so here's how you use it. The idea is I have some current, right? And I have a place P. And you can imagine some sort of coordinate system in the background, right? It could just all be an XY, or this could be a three-dimensional problem. So I'm going to imagine that along this line is a current I. And I am interested, just for the sake of figuring out how to use the Biot Savart Law, I'm interested in a really short segment of this wire right here. And it's a calculus segment of wire. So notice that the current is heading sort of up and to the right. So if I go and I look at this little segment of wire that starts here and ends here, it's pointed like this. And this is what ds is. And so I and ds are here. So what about r hat and r squared? R hat is a special vector. It's a unit vector. That is, it actually doesn't have any dimensions. It's pure direction. And what its job is to point from our little element of current and point at the place P where we want to know what is the magnetic field, right here, right? So this is the small contribution to the magnetic field from this little tiny segment of current. And the direction from where the current is towards the place I want to know the magnetic field, that's called r hat. That's the unit vector. What about r squared? So I'll do this one in purple. R squared is the square of the distance from the current segment out to the location where I want to know the magnetic field. So I'm going to have to divide by r squared. So it looks like an inverse square law, right? So the strength of the field from small segments ds of current I, the strength of the field falls off as 1 over r squared from that segment, just like electric field from a charge, right? Okay, so now you know what everything is. There is a current along a segment where the segment's direction is the direction of the current at the segment, right? Some vector. R hat is the direction that you must go in order to get from the segment to the place where you care about the magnetic field. And r is simply the separation distance, and that separation distance from the segment to the location P has to get squared on the bottom, right? So those are all of the parts from I ds cross r hat over r squared. Then there's a mu naught over 4 pi. So mu naught is a special physical constant. Mu naught is called the permeability of free space. Contrast this with epsilon naught, right? When we had electric field and we were calculating it, we understood small amounts of electric field because of a small amount of charge, and then there is this 4 pi epsilon 0, and then r squared and r hat. Really similar looking kind of expression, right? So IDS is a small length of current. dq is a small amount of charge. R hat points me from the small amount of current to the location in space where I want to know the magnetic field. That's what R hat did here. It points me from the charge dq out to the location where I want to know the electric field due to dq. And that electric field falls off as 1 over r squared. And this magnetic field contribution falls off as 1 over r squared. Here's a difference though. Epsilon naught is called the permittivity of free space, of the vacuum. Mu naught is the permeability. Epsilon naught showed up in the bottom, and mu naught shows up top. So that's different. But both of the expressions also share the quality of the 4 pi downstairs. Okay, so mu naught is called the permeability of free space, and mu naught has been determined to have the value of 4 pi. So there's another 4 pi, it's interesting, times 10 to the minus 7 Teslas meters per amp. Remember that, so here is the Tesla, and then there's a distance and a current. Okay, so just for the sake of completeness, if you calculate 4 times pi, it's about 12, because pi is about 3. It's a little bit bigger than 12. So this turns out to be about 12.6 times 10 to the minus 7, same units, Tesla meter per amp, right? Teslas times meters per amps. So those are the units of the permeability of free space. All right, so this is an introduction to Biot Savart. You can see that there's a cross product, which means the right-hand rule is important. And I made a right-hand rule reminder video, so that, you have no excuse, essentially, not to know how to use the right-hand rule. At this point, if you don't know, without a shadow of a doubt, how to use the right-hand rule, which is a very, very simple thing that's hard to learn when you are learning it for the first time, but becomes easier and easier, and you become faster and faster at quickly using the right-hand rule with just your brain. If you don't know how to use it, and you're not comfortable with it yet, you should learn how to do this before trying to learn anything else about the Biot Savart Law, because if you don't, then you cannot understand the Biot Savart Law. So that's the warning. It depends on the right-hand rule, and if you don't know how to do that, you're not learning your physics. So learn this first. Right-hand rule for cross products, right? And then you can begin to understand the Biot Savart. It's not going to go the other way around. Okay, next video, I'm going to show you some examples of using the Biot Savart to calculate the magnetic field of some current distributions.